Hello guys, and welcome to another calculus video. In this video we're going to discuss linear regression, and we're going to derive the formulas that you can use in order to find the best linear fit for your data sets. Now, I'm not sure if this is something that many of you will find useful. It's a little bit different from stuff we do on the channel, but it also is a pretty interesting look into multivariable functions, solving equations with sums, and also partial differentiation, which is a lot of fun. So without any further ado, let's go ahead and jump into the video. So if you have some data set where you have several y values and you have several x values, and they're not necessarily, let's say they kind of resemble a line more or less, but you have some data points that aren't exactly on that straight line. So I can kind of go ahead and guess and say that my line is going to be somewhat like this. Maybe it'll be y equals x, something similar to that. But as you can see, there's no way to get a linear equation which will pass through all of these points. So that's definitely not a perfect model. However, what I want to do is create an equation of the form y equals mx plus b that is pretty close to our data set values. So I want to minimize the error in between the line and the actual data points themselves. So let's say that the number of data points we have is n, and we can call our data points x1, x2, x3, so on and so forth, all the way up to xn. And we also are going to have y1, y2, y3, all the way up to yn, right? And so, x1, y1 is one of these points. So is x2, y2, and so on and so forth. And so what we want to do is we're going to try and minimize the amount of error between the line and these points. So the first thing we want to discuss is how we're going to be defining the error. And in general, the way that we do this is we use we're going to use the square of the residuals. So what this means is our error function, let's say our model is going to be y equals mx plus b. Then we want to figure out what the error is. So our error of our variables in this case are going to be m and b, since y and x are just our data points. So our error is a function of m and b, and it's going to be equal to the sum of from I equals 1 to n, right? Covering all our data points. And we want to get the difference between the data point and the actual value, right? And the model and the value, right? So that's going to be just y minus m x minus b, and this is going to be yi and mxi. And the trouble with this type of error is that this error can be kind of negative and positive, and so it's actually a little bit difficult because in general, when we're going to use derivatives and such to find the minimum point and to minimize the error, when we're searching for a minimum point, all we're going to find is the point which gives us the most negative error rather than the point that gives us the least error overall. So we're going to make this entirely positive, and we're going to do that by just adding a square in right there. So we're going to try to minimize the squares of the errors, right? And so all we need to do now is figure out how we can find the lowest point in this function e of m and b. So in general, when we're wanting to find the lowest point of a function like this, we're going to use derivatives, and we're going to try to find when the derivative is equal to 0. But in this case, we actually have m and b as two separate variables. So that means we need to find both a point where the derivative with respect to m is 0. So I'm going to write that as partial derivative of e over partial derivative m equals 0. And we also need the other partial derivative to be 0. And one really useful tool right here is, if we think about logically, in general, when we're searching for these points, we can have both of them be 0, and that can mean there's either a maximum or it could also, in theory, be a minimum, right? And that's kind of problematic for us because if we're finding the maximum amount of error, that's not really helpful to us. So instead, what we're going to do, but luckily we don't actually have to worry about that. And the reason for that is when if you think about it, when we're changing m and b, there's no real way to get a maximum amount of error at any point. Because if you keep increasing the slope or decreasing the slope, there's always going to be, you're going to stray further and further and further away from your data set in one direction or the other. There's no way where you can end up getting closer to the data set while, while increasing up to infinity, right? So we don't actually have to worry about finding a maximum point. We only have to worry about finding this minimum point. And in terms of stuff like saddle points, we will find that because of the simplicity of this function, you can see that it's second order in m and in b. That means we're going to have only one point where both of these partial derivatives are equal to 0. And so that rules out any possible saddle points because we know that this error does have to have a local minimum at some point. Just characteristic of it, it's quadratic in m and b again, so we know there's going to be a low point. So we don't have to worry about any sort of saddle points or other things. We don't have to use the Hessian matrix either. So basically, we know that once we solve for these zeros, we will have our local minimum point, and that will give us our linear regression model. So let's calculate these partial derivatives. Just using the basic rules of differentiation here, I'm bringing the derivative operator inside of the sum, which is totally okay because we're talking about a finite number of values. The derivative of multiple things added together is the same as the derivative of each of those added together. So it's just going to be sum from I equals 1 to n of yi minus mxi minus b. Then we're going to bring that 2 to the front, and we're going to multiply by, because we have chain rule, we're going to multiply by negative xi. I'm going to go ahead and reorganize this. This is going to be the same as negative 2 times this, or actually I'll do positive 2 here. 2 times the sum from I equals 1 to n of, we're going to have mxi squared plus bxi, and then minus xi yi, just multiplying that all out. Then we're also going to find the partial derivative with respect to b. So it's going to be a little bit simpler. Since we don't have to deal with much chain rule here, we're going to get negative 2 yi minus mxi minus b. And we don't have to multiply anything out right here. So if we go ahead and separate this, when I have the sum from I equals 1 to n, I'm just going to be denoting this just using that sigma, since it's going to be a little bit easier. So if we go ahead and expand this out, we're going to have two separate equations that we need to set equal to 0, right? This is equal to 0, that's equal to 0. So we're going to have, I'm just going to go ahead and get rid of the 2's by dividing by 2 on either side, just to make things easier. So we have m times the sum of xi squared plus b times the sum of xi minus the sum of xi yi equals 0. That's our first equation. And then on the bottom, we're just going to have the sum of yi minus m times the sum of xi. And then since we're just summing up b n times, that's going to be b times n minus b times n. So we can go ahead and solve. Usually I would solve using elimination, but since we're dealing with all these sums, I'm going to go ahead and just use substitution right here. So solving in this second equation for b, we're going to get that b equals the sum of yi minus m times the sum of xi all over n. So we already used that first equation, so I'm just going to go ahead and only copy down this second equation here. Just using substitution right here, we can go ahead and multiply everything out. M times the sum of xi squared plus b times, we're going to replace b right here. So we're going to have sum xi sum yi over n minus m sum xi squared all over n. And then we're also going to have minus sum xi yi equals 0. So if we go ahead and factor with respect to m right here, we're going to have m times the sum of xi squared on the inside minus the sum of xi all squared over n is going to be equal to the sum of xi yi minus the sum of xi times the sum of yi all over n. Sorry for my messing handwriting, as always, you guys know, but I will write the answer out pretty clearly. This is just pretty basic algebra. If we go ahead and solve for m, we're going to get that it's equal to sum xi yi minus sum xi sum yi over n over sum xi squared minus sum xi squared, just with the squared on the outside, over n. So this is our answer right here. I'm just going to keep b in terms of m since I don't really need to multiply all that out. So this is a pretty interesting result. There's not much you can draw from it in this form. I will let you guys know that you'll often see it written in a very different format, and that's an equivalent format. It looks something like they use y bar and x bar, so the average of x and y. And if you go ahead and multiply out all these sums and all the individual terms, you can go ahead and prove that they're equivalent. So that method is generally a lot easier, but this one is very easy to derive and use directly. So this is the formula that you would use, and this is actually also the formula that every computer uses when they make a linear regression. You can try it out for yourself in Desmos if you just go ahead and create a table of y and x values, and you can just like write them in, and then you write like y, this squiggly line, the tilde equals, and then any letter, so you could write m x plus b. It's going to go ahead and create a linear regression for you. And you can also try and match it up with this formula right here, and you would see that they will give you the same value. Another thing that I think would be really cool is if you have access to some sort of program to graph something, graph a function of two variables, and then you could graph the error function as a function of b and m, and then find that lowest point, and you'll see that this will match up with the values that we've just calculated. So I hope you guys like this video. I think it's a really cool way to use real life, very, very important calculations. This is something that gets used every single day. Real life applications of something as cool as partial differentiation and, sum notation and error, stuff like that. Personally, I haven't taken statistics, so I haven't seen much of this, but it's actually something that I've used outside of math a fair number of times. So anyway, hope you guys enjoyed the video, and I will see you next time.